Our next topic in summarizing quantitative data deals with measures of variability, or how spread out values are. So after defining what a typical value might look like in terms of like a mean or a median, we also want to know, okay, how much can we deviate from that? How much do the numbers differ from that sort of typical value? Now, some of the common statistics for measuring spread, okay, are very simple, but yet are not very useful mathematically. So for example, the range. Now it is very simple because it just literally measures how spread out are the smallest and largest values in your data set. So what it does is it takes the largest number, in this case 6,000 pounds, subtracts the smallest number, 2,750 pounds, and gets the range, 3,250 pounds. So the range of weights in the sample of automobiles turned out to be 3,250 pounds. Now, it really only depends on 2 data points. So the other 78 values in the data set are completely ignored. And also, if these values, either both of them or one of them, is an outlier, an unusually large or unusually small value in the data set, then it has a big influence on the value of the range. So as a result, the range really doesn't have a lot of real nice math features and is not very often used in terms of statistics. Now the standard deviation, on the other hand, examines sort of an average amount that the data values are located away from the mean. So you sort of start at the mean, the y bar or the x bar value, and in this case I'm going to call these y values and call the mean y bar. And then we're going to look at how far each data point is located from that y bar value. Okay, so we're going to do this with a small data set. So let's say that we have a data set of 4 points, 3, 4, 7, and 10. So let's go through and calculate visually what the standard deviation is going to be measuring. So in this case we need the sample mean. So what we have to do is add up the 4 numbers, 3 plus 4 plus 7 plus 10, get that result, which is 24, and then divide by 4. So y bar turns out to be 6. So what I did was I drew a number line and I labeled sort of where y bar was with a vertical line, and I also staggered where the data points were, 3, 4, 7, and 10. So this first point here, this asterisk, is where 3 is. So we're going to measure how far that is from the y bar location. 4, we're going to measure how far that is, and so on. Now in order to do that, what we're going to do is we're going to define a deviation as the y value minus the mean of 6. Okay, so we're always going to start with the y value and subtract 6. So in this case we would have 3 minus 6 for the first deviation, and that is -3. For the next one we would have 4 minus 6, and that is going to be -2. Now for the next value, we're going to have the value, right? 7 minus 6, and that's going to be 1, and that is positive. And then for the other one, we're going to have 10 minus 6, which is going to equal 4. Okay, so I'll pull that back one. So what I've done is I've sort of figured out how far it is between the asterisk or the data point on the number line and that mean by taking the y value minus the number. Now what do you get if you take -3 plus -2 plus 1 plus 4? Well, you get 0. So what this would suggest, that if I add up just the deviations, I'm going to end up getting 0. Well, if there's 0 variability, that makes it sound like, oh, there's no variability. None of the numbers vary from each other, so they would all be the same. But that's not true, because I have actually 4 different numbers. 3, 4, 7, and 10 do vary. They are different from each other. So just taking value minus the mean is not going to work. We need to sort of get rid of the idea that some are negative and some are positive and only deal with distance. Now the first thing you might think of is absolute value, but the absolute value function again has some properties that mathematically are not very nice that would appear right in the middle of the range of values I'm looking at the mean. So instead of doing that, we're going to square everything. Okay? So now what I'm doing is I'm actually creating something which is going to, whoops, what it's going to actually do is go back and look at, flip this back around here. We're going to square these things. And what I need to do is figure out how to get this thing. Okay, it's not popping up, so let me just do it this way. So what I want to do is square everything. So instead of being -3, that's going to be -3 squared, which will be now +9. But keep in mind, these are in squared units. So if this were miles or if this were dollars, now I'm talking about squared miles or squared dollars in these cases. Okay, so I'm just exponentiating. So then when I square that, I'll get 4 and so on. Then 1 squared is still 1. And then 10 minus 6 squared would be 4 squared, which is going to be 16. So now what I've got is squared distances from the mean. And the squared function is a very nice function to work with in mathematics, so that's why we really use it. But because I've squared everything, what I'm actually going to be calculating initially is a sum of squared variances, or sum of squared deviations, sum of squared distances or deviations from the mean. Okay, so all I'm doing is taking the sum of those numbers that I got by squaring things. So I'm adding them, so the answer is a sum, and it's a sum of squared deviations because I squared all of the differences between the numbers. So that actually turns out to be what? Well, 9 plus 1 is 10, 4 plus 16 is 20, so then that sums to be 30. But I don't want the total squared distances, I sort of want an average. Now this is where it gets a little weird. You divide by n minus 1. Okay, and the reason we do n minus 1 is because of some math properties. Okay, so for this to be a good approximation of the variability in the whole population, because a sample typically is not going to get the smallest and largest values that exist in a whole population, what happens is we have to divide by something a little smaller than n to get a good approximation. Okay, so what we're going to do is we're going to take 30 and divide by 3 in this case. So 4 minus 1, because there were 4 data points, equals 3, and 30 divided by 3 equals 10. But this is in squared units. Okay. 10 is called the sample variance. Okay. Which is denoted symbolically by s squared. Okay, so s squared is the sample variance, and that is 10. But what I really want is back in linear units, so that when I talk about the mean being in feet, then my measure of variability is not in feet squared, like an area of a carpet, how much carpet you need to lay down in a room, but rather is also in linear fashion, just one-dimensional. So what we do is we just take the square root. Okay, so S equals the square root of S squared, right? So S equals, and I can put a square root symbol in just to make it clear here. I want to take the square root of 10, okay, and then what does that turn out to be? Well, it's a little bit bigger than 3, okay, and that's sort of what I'm going to have to do. So this is where you would pull out your calculator, okay, and you would take the square root of 10 and then write the answer down. And that turns out to be, we'll just round it off to a couple of digits, about 3.16, and then that would be in whatever the units of measurement would be. So if I'm looking at amount of money in dollars that people had, that 4 people had in their pockets, well, the mean was $6 with a standard deviation of $3.16. Or if this was miles away from campus where you ate lunch on a certain day, well, the mean was 6 miles and the standard deviation was 3.16 miles. But in this case, they're both in linear units, whereas if we had the variance, S squared, that 10 would be in like square miles, which is really doesn't make a whole lot of sense in the context of what you're talking about, distance from campus. So keep in mind that we really are not going to do these calculations much by hand. Probably within the homework system they'll ask you to do something on it, but you can either use a calculator, to assist, but hopefully it'll be a real small data set and it really won't ask you to do it more than one time, hopefully. But the concept is understanding how to use it to make sense of what is possible and what is unlikely in a data set. And that's what we'll get into shortly in talking with something called the empirical rule later on, and when we talk about the normal distribution coming up in the next couple of weeks. Okay. Now let's switch gears, and basically finally we're going to consider something, another measure called the interquartile range. You might think inter is between, quarter is where sort of the root word that we're going to get quartile from, and then range is sort of distance between those things. So this is going to be distance between a couple of the quarter dividing points in a data set. Okay, but let's talk about quartiles. Now, a quartile is a value which is going to divide data into some aspect of quarters, right? Because that's the root word. And there's actually 3 ways we can divide a data set into quarters, right? So you've got the first quarter, second quarter, third quarter dividing points, okay? Now, we've already discussed the median, and that would be sort of like 2/4 of the values of the data are below it. The other 2/4 or half of the data values are above that. Okay, so that's sort of your 2/4 is a half. So the median is actually the second quartile. Now, if you take the first half of the values in a data set, those that are at the median or lower, and divide it in half again, you've now divided the first quarter from the second quarter of the data values. So roughly 1/4 or 25% of data values are going to be equal to or lower than the first quartile. So obviously that means the other part, the 3/4 or 75% of values, are above it. Similarly, there's a third quartile. So if you take the upper values, upper half of data values in a data set, and divide it in half, just like you did with the median, so take the median of the upper half of the data set, now you've got a third quartile. So 3/4 or 75% of the data values would be at the third quartile or lower, while the remaining 1/4 or 25% of the data values would be at the third quartile or higher. So basically what you would have is you'd have the first quarter of the data, and this is putting the data in order, obviously. So you have the first quarter of the data, then you have the location of Q1, the first quartile. Then the next quarter of the data, and then you have the median. So where the median is, half the data is below it, half the data is above it. Then after that, you have the next quarter of the data, and you come to the third quartile, and then you have the last quarter or last 25% of the data values. Now the interquartile range is simply the distance between the first quartile and the third quartile. Now notice that accounts for 2 quarters of the data. So what the interquartile range, or IQR, is doing is actually measuring how spread out is the middle 50% or 1/2 of the data. So it gives you a measure excluding possible extreme values, outliers or tails of distributions, but it just looks at the middle 50% of values and says how spread out is the middle half of the data values. So the interquartile range defines just how far that middle half of the data extends. How spread out is it? Okay, so it can be very useful, especially when you have outliers that would influence maybe the standard deviation or range measurements, whereas the interquartile range just looks at the middle half of the data and how compact or how spread out it might be. So that is the conclusion of measures of variability in terms of data sets. Now, just to mention, typically what happens is if you have a histogram or a data set which is symmetric, so it looks like a mirror image, you use the mean to measure the center, and you would use the standard deviation to really measure the variability or the how spread out the values are. If on the other hand you have data which is heavily skewed or contains outliers, usually you're going to use the median for the measure of what is typical or the center, and you'd use the interquartile range for what is sort of the measure of spread or how spread out the values are. So just keep in mind, symmetric, use the mean and the standard deviation. For non-symmetric, highly skewed data, you're going to use the median and the interquartile range.